In this problem, we will go over the analysis of a vortex tube and evaluate how it's able to separate one stream into a hot and cold stream without violating the second law of thermodynamics. And so we're dealing with an ideal gas that's going to enter in a vortex tube with an inlet pressure 1.5 atm, inlet temperature 25 degrees Celsius, and an inlet mass flow rate of 1 mole per second. We're told that this inlet stream is going to go through the vortex tube, and it's going to be split into two streams, where the stream at the left side comes out at a cold temperature, Tc, that's less than the inlet temperature, and the stream on the right side is going to come out at a hot temperature, Th, that's greater than the inlet temperature. Both streams are going to emerge at atmospheric pressure, and for this problem, specifically, they're going to have the same mass flow rate. We're also told that the molar heat capacity, constant pressure, is going to be equal to 27.44 joules per mole Kelvin. What we want to find in this problem is we want to find the maximum temperature difference between the hot and cold outlets. What's the biggest delta T we could have between TH and TC? And then we want to evaluate why the vortex tube is able to separate out these two streams without violating the second law of thermodynamics. Based on this problem description, I want you to pause the video here and I want you to sketch out the system. Okay, based on this problem statement, we could sketch out a diagram that looks like this. So we have our vortex tube, we have our inlet going into the vortex tube at these inlet conditions, and then to the left side of the tube, we're going to have our cold stream, which we're told it comes out at atmospheric pressure, but we don't know its exact temperature, which we're going to call Tc. And we don't know its mass flow rate, though we're told the mass flow rate between the cold and the hot streams are going to be equal. On the right side, we have our hot stream. We know the pressure, we don't know the temperature. Okay. And we're told the heat capacity of this ideal gas. All right, so we're dealing with three unknowns, and so that means we have three equations that we need to deal with. Before we could go through our balances, we need to define our assumptions. So mass is crossing the system boundaries, so we're dealing with an open system. None of the variables are changing with time, so we're going to treat this as a steady state problem. We're not going to worry about changes in kinetic or potential energy. For the vortex tube, there's nothing spinning inside of it. There's no moving parts or anything. It's just the ideal gas is passing through it. And so, when it comes to shaft work, we're not going to have any. Right? We should also declare that we're dealing with an ideal gas. Right? Also, with the vortex tube, we're going to treat it as adiabatic, right? There's no heat loss from it or anything. So, in addition to the work being 0, Q dot's also going to be 0. Now, there's one other assumption that the problem hints at. And so what it's asking us is it wants us to find the maximum temperature difference between the hot and the cold outlets. And so in order for the maximum temperature difference to occur, all of the energy that comes in with the inlet stream has to be split up between the cold and the hot stream. None of that energy can get lost, right? It can't get lost as heat. Furthermore, that energy can't go towards creating more entropy in the system. And so, when it asks us to get the maximum temperature difference, essentially what it's telling us to assume is that the process is reversible, right? Once again, all the energy coming from the inlet stream just gets split up between the cold and hot streams. None of it gets wasted. None of it goes towards generating entropy. And so what this tells us to assume is that the Sgen in our entropy balance is going to be 0. Okay. All right. other things to state, and specifically for this problem, so hot and cold streams have same molar flow rates. So just to clarify, only valid in, I'll move it to the next line, only valid in this problem. And in general, it's not true general for vortex tubes. So in other problems, such as the one that you'll do on the homework, the flow rates of the cold and hot stream will not be equal to one another. So you'll actually have to solve for that through a material balance. But for this problem, it's just telling us to assume it. And the last sort of thing we'll declare in our assumptions is our reference conditions. So just like we've been doing before, whenever we deal with an ideal gas problem, we're just going to use the inlet conditions as our reference state. Okay? All right, so now that we've declared all of our assumptions, we'll now just proceed through our different balances. So for the material balance, steady state, no reaction. Therefore, inlets equal to outlet, or inlets equal to N1, or, let me move this over, inlets equal to N1, outlet is equal to N2 plus N3. But remember, in this problem, we're assuming that streams 2 and 3 have the same molar flow rates. This is just going to be N2. So if we go to our material balance, we get N1 is equal to 2N2. Therefore, N2 is equal to 1/2 N1, which means it's equal to 0.5 moles per second. And that value is also equal to N3. Okay. All right, so from the material balance, we figured out all the molar flow rates. Let's now proceed to our energy balance. Open system energy balance. WS. So alpha I plus 1/2 UI squared plus GHI. Okay. Steady state, whole left side goes away. Okay. We don't have any heat, we don't have any shaft work, we're not worrying about kinetic or potential energy changes. And so really, in our energy balance, all we have is that we have the energy of the streams going in. And here I'm writing it in terms of molar enthalpies. So that way I could write the molar flow rates instead. We have N2, H2, N3, H3. From the material balance, we know this is 1/2 N1. Okay. And because this equation is equal to 0, and we have N1s in front of everything, that means we could factor out the N1s and cancel them out. And so from our energy balance, what we get is that the left-hand side 0, and we just have H1 minus 1/2 H2 minus 1/2 H3. Okay. All right. And so our energy balance just simplifies down to this. And so now what we want to do here is one of our main goals is to figure out what these temperatures are. And so we need to relate our enthalpies to temperatures. And so we're going to do that just by using the constant pressure heat capacity. Okay. So zoom in a bit. For H1, integrate this from CP from a T reference to T1. And for now, I'm actually just going to just leave the T reference in. You'll see why I do that in a bit. H2. Similarly, if you integrate, you get this. Okay. All right, so we have all our enthalpies. One thing I want to point out here, when it comes to the enthalpies, we're accounting for differences in temperatures. But remember, in this problem statement, the ideal gas is entering at 1.5 atm and leaving at 1 atm. But there's nothing in our enthalpy calculation that involves pressure. So I just want to emphasize here, changes in P don't affect the enthalpy for ideal gases. So this is specifically for ideal gases. As you'll see, as we get into chapter 6, when you're dealing with a non-ideal gas, pressure can play an important role. Okay? All right, in any case, so now that we have the functional forms for the enthalpy, let's plug it in. So we have CP T1 ref minus 1/2 CP T2 T ref minus 1/2 CP T3 T ref. Okay? Okay. What I'm going to do is I'm going to rearrange this equation. So I'm going to combine all the terms involving T1, T2, T3 into one set of parentheses. And then I'm going to combine all the terms with the T refs into another set of parentheses. You'll notice here we have T ref minus 1/2 T ref minus 1/2 T ref. That's going to cancel out, right? So essentially, in this problem, just based on how the math was arranged, it didn't matter what a T ref was in the end, right? All that stuff's going to get canceled out. And here, we could factor out the CP, or we could divide it out. We could get rid of that. And so what we find is in the end, we get a relationship between the inlet temperature and the outlet temperatures. Of course, at this point, we have two unknowns, right, and only one equation. And so that tells us we need another equation in order to solve this. And so to proceed, we just go to the entropy balance. So open system entropy balance equation, ds dt. We have the entropies of stuff going in, entropies of stuff going out. Then we have the heat term, and Sgen. Okay, we could simplify this entropy balance down. Steady state, adiabatic, reversible. Okay. All right, and so what we're left with so far with the entropy balance is just the entropies, in this case the molar entropies of stuff going into and out of the system. And just to emphasize, same thing we saw before, this is 1/2 N1, 1/2 N1. Since the left-hand side is 0, we can factor out the N1s and they go away. All right, so at this point I'm going to call this equation 2.